Okay, we're now going to do the second part of this question, so let's read it together. Another student suggested, take it to the roof and lower it on the end of a piece of string until it reaches the ground. Then measure the string's length. This is known in maths as a joke. Acknowledging those students' humour, a third student gave himself a challenge by using a bit of both. His proposal was A. Climb partway up the Clarendon Building and use the string method to find the height where you are, h2 meters. Then, time the barometer's fall when dropped by the first student, but from the instant it passes your height to the instant at which it hits the ground. Formulate the third student's method by expressing h1 as a formula in terms of h2 and t2 only. So the key to this question is going to be getting that information deciphered down into a sketch and working through our SUVAT's formulae using what we know we've found expressed in the way that the question has given it to us. So we've been told to define our h2, our height that we've climbed, as this. Okay, it's a distance from the ground that we've climbed up. That's our h2. So our barometer's been dropped from up here with a velocity of 0. It's got to our height at a certain velocity. Now, irritatingly, because of the way the question's been set up, I can't call that velocity v1. It's at h2, so I'm going to call the velocity v2. Even though, irritatingly, it's actually going to be at v1 in our definitions from the first part of this question, as that's after it's travelled the distance h1. We can't get around that. We just need to make sure we're okay with it. So I'm saying the velocity at the point where it's at the height h2 is going to be v2, and the velocity when it hits the ground is going to be a v1 because it's now travelled a distance of v1. We still know our gravitational acceleration, which we were told we can simplify to be term ms to the minus 2, and we're still going to define down as positive, seeing as that's going to make most of our work in positive and life a little bit easier as a result. So what should we do here? Well, it doesn't hurt to look at look at the context of the question and the bit that the question is focusing on. The bit the question is saying we're going to time the period it takes to fall from how high we've climbed, this h2, until when it hits the ground. So I'm going to call that time t2. I'm defining that time t2 as the time it's taken to fall from the time we've measured to the ground. And the distance is h2 by the definition given in the question. The velocity at the point we start measuring we don't know, so we're going to call that v2 for the velocity at v2 like we've already said. And the velocity at the ground is v1 if we're consistent from the first question, and the acceleration, hippity hooray, we actually know that as a number, it's 10. So it's time to start considering which SUVAT formula we should use. Is it going to be v equals u plus at? Is it going to be v squared equals u squared plus 2as? I think the most sensible formula to use would involve s, as we're asked ultimately to express in terms of h2, and involves t, as we're asked to ultimately express in terms of t2, and tries to use as many of the things that we also know, like a, as possible. So I think the most sensible formula to use is that s is equal to ut plus a half at squared. There's one issue here, isn't there? And that's that we don't know what that u is. U being the initial velocity in that time period we're considering. We're defining it as v2, but we don't know what that is yet, so that's going to be a problem we're going to have to solve. But aside from that, this is good because we know that our distance is h2, which we're told we can just take as a value that we know, and that's equal to our u, which we can only call v1, v2 excuse me, times t2. plus a half times R10 times RT2 squared. Now I'm going to rearrange this so that V2 is this subject, because as long as we can get rid of that V2 by perhaps substituting into another formula that we can create, which only involves T2 and H2 and H1, then we're going to be able to express our H1 in terms of T2 and V2 and T2 and H2. So if I subtract a half T2 squared, which will be the same 5 T2 squared, I'd get H2 minus 5 T2 squared here, and then if I divide it by T2, I'd get an equation with V2 as the subject. So we now need to consider, how can I get rid of this V2 by substituting it into another equation that I can form, which has V2 in but nothing else in. So what we should really do is consider anything else, any other equation we could make here. And so it would be sensible to consider perhaps the first leg of this journey. Now we didn't measure the time for this, but we do know some important information about this first bit. For example, we know that the initial velocity is 0, and we also know we can express this height in terms of H1 and H2 is H1 minus H2. You might have been tempted to call that H3, which isn't the worst thing in the world, but if you can avoid making extra variables, then do so. So we're now going to consider our suvat for this first leg of the journey from the top of our Clarendon Building until the height that we climb to. So if I write out my suvat again, well, S, the distance, is going to be H1 minus H2. The initial velocity, we thankfully know, and it's 0. The final velocity for this leg of the journey is going to be V2. The acceleration I know is 10. And the time, we haven't actually defined the time, it's the time it takes to go from 0 to this point here. I guess we could call that T1 minus T2, where T1 is the total time it's taken, like we defined in the first question. That way we're not creating a new time again. And we need to consider which is the correct formula to use. Should we be using S equals UT plus a half AT squared here? Should we be using V equals U plus AT? Should we be using V squared equals U squared plus 2AS? Etc. Well, let's have a think about it. We are trying to get a formula which just involves the velocity, the final velocity that is, the H2 value, the H1 value, so that would be our S in this context, and the T2 value. Well, if I involve time in this, then I'm also going to be bringing in T1, which is a measure I've not got any bearing on. I started my stopwatch when this barometer was already falling and falling past me. So I'm going to have to use one of these which doesn't involve time. I'm going to use V squared equals U squared plus 2AS, which is going to be quite nice actually, because the U squared is going to become 0. So I can say that my V2 squared is equal to 0 squared plus 2 times my acceleration, which is 10, times my distance, which is my H1 minus H2. And actually I know what V2 is, I've expressed it here. So I can say that my H2 minus 5T2 squared over T2 all squared is equal to, simplifying this is going to be 20 H1 minus H2. And now all I need to do is to make H1 the subject of this. So if I expanded my right hand side out here, I'd get 20 H1 minus 20 H2. So if I now choose to add my 20 H2 and divide by 20, I'm going to have expressed H1 in terms of just H2 and T2. So doing so, I'm going to have H2 minus 5 T2 squared over T2 plus 20 H2 all over 20 is equal to H1. Now I suspect that there's a quite a nice way to arrange that. We could at least have a quick look at it, couldn't we? Don't forget a squared there. So that's going to mean my H1, we can at least simplify their 20ths out here, can't we? So that's going to be 1/20 of my H2 minus 5 T2 squared over T2 all squared plus a 20th of 20 H2, so plus H2. And that's our answer.